And we're back in better than ever in 7.2, ionic bonds and ionic compounds. In this section we're going to take a look at how these ions that we talked about in 7.1 bond together and what some of their properties are. An ionic compound is simply a compound, let me get my pen here, it is a compound composed of cations, which are the positively charged ions, and anions, which are the negatively charged ions. And when they come together, they form what are called ionic bonds, and ionic bonds are simply the electrostatic charges holding the ions together. Simply meaning this: positives and negatives are attracted to one another. And so because you have a positive and a negative, they're going to stick together. Now realize that these compounds, because you're going to have a balance of charge, though you do have positive and negative areas in the compound, these things are electrically neutral. Alright? So, let's talk about how these things form. Let's scroll down a little bit. In 7.1 we learned that metals tend to lose electrons to gain a noble gas configuration, while nonmetals tend to gain electrons to achieve a noble gas configuration or to complete an octet. And so if you take a look at sodium, sodium has 1 valence electron. Chlorine has 7. Well, what's going to happen is sodium is going to donate one of the electrons, its only valence electron, over to chlorine. And so sodium will be left with no electrons in the third energy level, meaning that it now has a complete second energy level in the outermost or the highest occupied energy level. Chlorine, which was 1 short, now has filled the third energy level, so it also completes the octet. In doing so, sodium becomes positively charged, chlorine becomes negatively charged, we now call it chloride. And so now they both fulfill the octet, and they are both attracted to one another because one is positive and one is negative. Alright? When that occurs, you get a formula of NaCl, which would be its chemical formula. However, this chemical formula does not represent a discrete molecule. Rather, what happens is that because they're positive and negative, let me scroll down here, they form these crystals. This is going to be the sodium. I'm going to have to change colors here. Let's go to, let's say, a red. You should be able to see that. If this is the sodium ion, positive, this will be the chloride ion, negative. But this positive is going to attract other negatives to it. And this negative is going to attract other positives towards it. And so what you have is a three-dimensional lattice of positives and negatives repeating one another. So we have what's called a formula unit, which is just simply, let me go back to the green here. It is the lowest whole number ratio of the elements. Alright, the lowest whole number ratio of the elements in the compound, or of the ions, because we are dealing with an ionic compound here. So when we say that sodium chloride is NaCl, that means if you take a look at the crystal, for every 1 Na you're going to find just 1 Cl. Alright, and that is the repeating unit, NaCl, 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 in 3 dimensions. Now, not all ionic compounds have a 1-to-1 ratio. Some are 2-to-1, such as magnesium chloride, where you're going to find 2 chloride ions for every 1 magnesium in the repeating structure. Alright, now scrolling down. These ionic compounds are going to have particular properties that are characteristic of ionic compounds. For example, for the most part, ionic compounds are going to be crystalline solids. at room temperatures. All right. Number 2, they're going to have high melting points. The reason why they have the high melting points is because it takes a tremendous amount of energy to separate a positive from the negative charges. These are very, very strong bonds, and so in order to get those things to separate and start moving around one another, you have to put a tremendous amount of energy into these things. Going back to the crystalline solids, the reason why they form crystallines is because they can actually keep adding additional ions to their outermost edges of the solid. So you can actually grow these things by just simply adding more and more of the ions, and they'll fall into place. So they form crystalline structures. They have high melting points. They have a characteristic coordination number. I'll show you what the coordination number is in just a second. And finally, they will conduct electricity when melted or dissolved in water. All right. So now let's talk about the coordination number here just for a second. We're going to need to scroll down or flip the page. The coordination number is simply the number of ions that is surrounding a given ion. For example, let me go back to red here so we can see this. This is the sodium ion, and if you notice, surrounding each sodium is going to be 1, 2, 3, 4, going down, 5, and up, 6 chloride ions. All right, so the coordination number for sodium is going to be 6. If I switch this up to blue, the chloride ion also experiences the same thing. And the way they have this drawn, it'll be a little bit difficult to see, but if you notice the chloride, here's the chloride ion. Let me change this over to blue now. You have 1, 2, 3, back to the middle, 4, going down, 5, and then when you go to the next unit, there will be another one over there, 6. So in the case of sodium chloride, the coordination number for both the chloride and the sodium are going to be 6. As we scroll down here, if you take a look at cesium chloride is put together a little bit different. Here's the cesium atom. Cesium is surrounded by 1, 2, 3, 4, 5, 6, 7, 8 chloride ions. So the coordination number for cesium is going to be 8. And in fact, though they don't draw this in here, it is the same thing for the chloride ions in this case. The chloride ions are also surrounded by 8. But the coordination numbers does not have to be the same for each ion in a particular structure. If you take a look at titanium dioxide or titanium 4 oxide, it goes by the name rutile or rutyl. Let me change colors here. Let's go with yellow. If this is going to be your titanium right here, titanium in this case is surrounded by 1, 2, 3, 4, 5, 6 oxygens. However, the oxygen atom or the oxygen ion is actually only surrounded by 3. And again, they don't show it real well in this particular diagram, and that's not important for us. But you should know that in fact each ion has its own coordination number. And there's a whole branch of chemistry that deals with coordination chemistry, particularly when they're in solution. Okay, and then finally, the last thing that we want to mention is the fact that ionic compounds will in fact conduct electricity. The reason why is the charged particles. Charged particles will conduct electricity. So if you dissolve them, they break up into their individual ions, and that will conduct electricity. Or if you melt them, the ions are free to flow around and move around, so that will also allow them to conduct electricity. All right? So, you should simply realize that ionic compounds are put together by ionic bonds, which are electrostatic charges between opposite charges, positives and negatives. They have characteristic properties, such as being a solid crystal, high melting points, they have a coordination number, and they can conduct electricity. All right? That concludes 7.2.